Exponential and logarithmic equations and the change of base formula with examples. So we're going to go over some properties, change of base formula, and examples. Properties of logarithms. Number 1. Log 1 base b equals 0. Since b to the power 0 equals 1. Anything raised to the power 0 equals 1. And that's how we read exponential from last time notes. Second one. Log b base b equals 1. Differently, we could say b to the power 1 equals b. So just to confirm that this is true, b to the power 1 equals b. Number 3. Log the product of x and y will be the sum of two logs, one for x and one for y. It's almost like saying it like you're going to distribute the log, but you're going to have a plus sign in between them. Keep that in mind. Number 4. Log the quotient of x and y will change to log x minus log y. So in case of the product, it's a plus now here. This is called expanded form, and this is called single form. This is also called expanded, and this is single. So subtraction comes from division, and addition comes from multiplication. Number 5. If you have a power inside as x to the power a, you could move this a all the way up front. It becomes a log x base b. The new rule for this section was not mentioned last time video is number 6. It's called change of base formula. Log c base b equals log c base a over log b base a. Notice that I wrote the base a for both the same in color. Just want to make sure that when you change log c base b to two logs, you use the same base. For the convenience, we use a equals 10 because our calculators do the log base 10 for us, and that's our system base 10. Now keep in mind the conditions here says that a and b and c, they have to be positive. The bases here, the base is b, here the base is a. They cannot be 1. Alright, just keep that in mind. Change of base formula in logarithms. The change of base formula allows you to calculate the value of a logarithm by rewriting it in terms of a different base. So if you have a base of 5, a base of 7, a base of 8, your calculator does not do that. When you change to base 10, becomes handy. We're going to see some examples. The change of base formula states log c base b becomes log c over log b with a new base now called base a. As I said, for the convenience, we're going to pick log base 10 instead of a, where a is greater than 0, b is greater than 0, and c is greater than 0, and a cannot equal to 1 and b cannot equal to 1. Here's some practice changing from logarithmic form to exponential form and the other way around. The general form, the way it looks like with letters, is as follows. Log c base b equals a could be written in exponential form this way: b to the power a equals c. Let's go back and look at it from here. B to the power a equals c. Keep that in mind. B to the power a equals c. B is the base, B is the base, to the power a. So the one on the right side goes on top as an exponent. The inside part C is called the argument. Let's practice. If you have log 8 base 2 equals 3, how could you write this as exponential? Try to follow this rule. I'll give you like a few seconds to think about it. Read this, apply it here, and think, what should I write here? Okay, gonna give you a hint. We're gonna go this way, back this way, with those in mind. One more time. This. So 2 to the power 3 equals 8. Let's see that. Yes. Let's try another one. Log 1 base 10 equals 0. As an exponential form, will read as, okay, 10 to the power 0 equals 1. Yes. One more. Log 9 base 3 equals 2. As an exponential, it's gonna read 3 to the power 2 equals 9. Now let's try the other way around. Here's an example. 10 to the power 2 is 100. That's called exponential form. To write it in logarithmic form, I'm gonna put the base 10 and think as if I'm reading it in exponential. So I'm gonna write log right here, base 10, and think this way. 10 to the power what equals what? 10 to the power 2. 2 should go all the way outside. Here we go. Log 100 base 10 equals 2. One more. 5 to the second equals 25. As a log form, it's going to be log. What's the base? The base is 5. After the equal sign, it's going to be the exponent, which is 2. Here we go. 5 to the second. 5 to the second equals 25. One more. 3 to the power 3 equals 27. That means log base 3 to the power 3, and the argument inside will be 27. Okay, now let's go back and look at it. Went too fast. Alright. Let us test the change of base formula. See how it works, if it works. Let's use some numbers. We're used to the hundreds and tens and 10 to the seconds 100 and so on. So let me use those numbers. For the convenience, let a equals 10, base 10. Log 1 million base 100 equals what? Let's call it x. So we need to find the exponent x, because we read this as 100 to the power x equals a million. Notice that we put commas to read the zeros quicker. We have 6 zeros. Keep that in mind. So it's 100 to the power x equals a million. I think when you multiply 100 by itself, how many times do you get a million? Count the zeros. Pay attention to the zeros. 100 to the third is 100 times 100 times 100. You add the zeros and becomes 6 zeros, so that should do it. So what's x? X equals 3. Now let's try to test that if it works this way. We are looking at the left, log c over log c base b as log c base b. All what we did here is, if c is a million and b is 100, what is that? That came up to be 3. I called it x, then I solved it x as 3. Let's do the change of base formula, and hopefully we'll get also 3. Now let us use the change of base formula. Log a million base 100 is log a million base 10 over log 100 base 10. But that says 6 because 10 to the power 6 is a million, and that says 2 because 10 to the power 2 is 100. Simplify 6 over 2, you get also 3, and that should explain how the change of base formula works. Let's derive the change of base formula. Starting with log c base b, I want to call it x. So let's make it equal to x. I have log c base b equals x. Write it in exponential form. We know how to do that. B to the power x equals c. Now b to the x equals c. We're gonna apply log to both sides. Here we go. Apply log base 10, of course, to help us do it quick and use a calculator. So I have log of b to the x equals log of c, of course, base 10. Now I'm going to use property number 5 and move this x all the way to the front. It moved, as you can see. I moved the x all the way to the front. Leave x alone, that means divide both sides by log base b. Divide both sides by log base b, and to leave x alone. I end up with x equals log c over log b. We said earlier, let's call it x, so log c over base b equals x, and we ended up with x equals log c over log b, so they are equal, and that is the proof. So here's in short as a summary: x equals log c base b, also x equals log c over log b, or in short we call it log c over log b without saying base 10. Log base 10, in short we call it log, and it's called the common log. Your calculator does not display the 10, you will see log by itself, meaning log base 10. So that ends the proof of the change of base formula. Now, examples on the change of base formula. Number 1, solve 20,000 equals 50 times. Looks like this is an x, but it's actually times. 50 times 3 to the power t minus 1 for t. We're gonna solve for t. To reach out to t is not quick. It's not like simple algebra. So let's get rid of 50 first out of our way. We're gonna divide both sides by 50. Divide both sides by 50. I get the following: 50 cancels from the right side. On the left side, simplify 20,000 over 50, cancel 1 0, and you end up with 400. Now we're ready. We could change this to logarithmic form. Method number 1, I have two methods. You don't have to use both, but the first one is what your book is using, which is called the change of base formula. Okay, let's go over method number 1. Rewrite the exponential form in logarithmic form. So we're gonna read this as a log base 3. Here we go. Log base 3 reads 3 to the power t minus 1 equals 400. So we did it right. Next, we're gonna use the change of base formula. So what's log 400 base 3? It's gonna be log 400 over log 3. To do this, you just use a calculator. Now we could use a calculator. Earlier, you can't find this using a calculator. because your calculator does not have base 3. It only has base 10, which is called the common log. So using the calculator, I got approximate to 5.454, and this is how it looks on the calculator or the graphing calculator. So 4 digits will be fine. Of course, round to 4 digits. 6 is too high, so the 3 has to be 4. 4, 5, 4. Actually, I did for 3 digits. Alright, now go back to the problem and place the left hand side with this much. So we have 5.454 is approximate to t minus 1. Add 1 to both sides. Alright, you get t equals 5.454 plus 1, which is 6.454 approximate. Done. Let's take some more examples. Or actually, method number 2. I forgot about method number 2. Method number 2 is a little bit different, but it ends up the same. So we have the following: 400 equals 3 to the power t minus 1. And now I'm going to apply log to both sides. Move t minus 1 to the front. This one here, move it to the front, which is rule number 5. T minus 1 to the front. I have it this way. Divide both sides by log 3, and it ends up like the previous method. It's not called change of base formula, but once you divide, look at the left hand side. That's similar to last method. Looks like we went around to make it look like the last time, log 400 over log 3, and the rest of the steps will be similar. Same thing, same steps. Alright? Okay, another example. Solve 6 to the power x minus 5 equals 24. This is ready. I don't need to add or subtract first, so I could just rewrite it as as logarithmic form first. Rewrite the exponential form in logarithmic form. We know how to do it. It's a log, and the base is 6, and the argument is 24, and the exponent is x minus 5. Let's apply now the change of base formula. Use the change of base formula to on the left. It's going to be log 24 over log 6. On the left, log 24 over log 6. With the calculator use, we get the following: approximate to 1.774. So we replace that on the left, and we write approximate. Add 5 to both sides, and that should do it. And we're done with this problem. So it's approximate to 6.774. One more. Solve the following. In this case, we need to get rid of the 3. It's in my way because I can't rewrite this exponential as logarithmic yet. The 3 is in the way. Subtract 3 from both sides before you change to logarithmic form. Okay, we do this. We end up with 70 on the right side and a clear power on the left. Now change the exponential form to logarithmic form. So it's a log with base 14, and the argument is 70, and the exponent is x minus 6. Let's apply the change of base formula on the left. Alright, becomes log 70 over log 14. Use a calculator on the left. Just type it correctly and practice to see if you do it right. It's approximate to 1.6099, and we equal this to x minus 6. Then we add 6 to both sides, and that will end up the problem. x is approximate to 7.6099. Another example. Solve the following logarithmic equation. Check your solutions or answers. It's given to me as log base 6. Now what's inside, which is called the argument, is x to the second plus 5x. Do I use the change of base formula because that's not gonna help. I'm not gonna rewrite this as log x to the second plus 5x over log 6. I can't use a calculator for that. So I'm gonna rewrite this as a exponential form. I'm gonna go 6 to the power 2 equals x to the second plus 5x. Here we go. Rewrite the logarithmic equation in exponential form. It reads x to the second plus 5x equals 6 to the second. 6 to the second, that means 6 squared, which is 36. We're gonna move everything to the left. Subtract 36 from both sides. I get x squared plus 5x minus 36 equals 0. Factor it. I get x plus 9 times x minus 4 equals 0, which implies that x equals -9 or x equals 4. Okay. Now it says check your solutions or answers, so you have to be careful, and let's do that. Check. When x1 equals -9, I want to go here and plug in -9 and see what do I end up with. So I'm going to take x to the second plus 5x and use x value equals -9. I want to see if this is going to end up true. So the argument inside is x squared plus 5x. Plug in -9, I end up with 36. So that is 36, and it's gonna look like this. Yes, log 36 base 6 equals 2, which is true. Why? Because 6 to the second is 36. So we're good. Let's go for x2 equals 4. This should be 4, not -9. Just be careful. Plug in 4. 4 to the second plus 5 times 4. It's 16. That's 4 to the second. 5 times 4 is 20. Also 36. So yes, 4 also works. So they're both correct. Alright. Another example. This one is a little bit different, so we have to be careful. Use the properties of logarithmic or logarithms to solve the following logarithmic equation and check your answer or answers. First, the 2 is out. We're going to take it back in. So let's see how we could do that. Apply property number 5 and move the 2 in, back in, on top of x in the first term. Okay, we did that. 2 is back in. Now this is a subtraction between two logs. That's called expanded form. We need to write it as single form. I'll give you a hint. Either it's coming from division or it's coming from a product. Subtraction between two logs comes from a division quotient. So let's do that. Apply property number 4 on the left and change the subtraction to division. Okay, we got that. That's log, one piece of log right here, x to the second over 4. Okay? Now, this is something also new. Log base 5 of something equals log base 5 or of something written differently. What does that mean? It means that x to the second over 4 and 8 minus x are equivalent. Why? If log a equals log b, that means a equals b. Think about it. I mean, if I say log 7, can I say equals log 6? Of course not. Log 7 equals log 7. So if they're written differently or hidden as a and b, they should be equal. So now we're using algebra. We got rid of the whole log expression here or equation, and we changed it to regular algebra. Multiply both sides by 4 to get rid of the fraction on the left, and I get 4 cancels from the left. On the right side, I'm going to apply the distributive property. 4 times 8 minus x becomes 4 times 8, which is 32, and 4 times minus x, and that is x squared equals 32 minus 4x. Let's move everything to the left. When you move it to the left, you have to change signs. So 32 is positive now, becomes negative, and negative 4x becomes positive 4x. Okay, x squared plus 4x minus 32 equals 0. Now we need to factor it. To factor this, we start with x, and 32 will go like 16 times 2. That's too high. It's not going to give me a difference of 4 or a sum of 4. 8 and 4 will do. 8 times 4 is 32, and we have from n right here negative 4x, and positive 8x combines to positive 4x. So we have two x's. x1 equals 4 and x2 equals negative 8. But they told me to check answers, so I have to be careful. So we have to, I can't stop right here and say I'm done. I have to be careful with what they are saying here. Let's apply it. I'm going to take the first number 4. All what I'm going to do is I'm going to write the equation and think if I plug in 4 where x is, if the equal sign is going to be valid. So I have log 4, 8 minus 4 is 4. This one right here in green I wrote 1. I just want to see that this log 4, I have 1 of it. Because this one is also log 4 and I have 2 of them. So 2 of log 4s minus 1 log 4s will be 1 log 4. But the right hand side is log 8 minus x, where x is 4, 8 minus 4 is just 4. So log 4 equals log 4, and we're done. That's for the first x. For the second x, we're almost done, which is negative 8. Plug it in here for x, plug it in here for x. That's going to be 8 minus negative x, negative 8, which is 8 plus 8, which is 16. But here, that's a problem right here. There is a problem right here that you have to be careful. You might keep going and simplify, but as I said, just be careful. On the left, that's what I have. We cannot move on because we have in the first term a log of a negative number. Log negative 8 is undefined. You could test it on a calculator and there is more support why we don't have such thing as called log negative 8. If you graph the log is the inverse of exponential functions. It goes only to the right. Of course, if it's not shifted, as you could see, the domain is x is greater than 0. It only lives to the right side of the y-axis. You cannot plug in negative 8, and you could test it on the calculator. Try on a calculator, for example, log negative 22 base 10, of course. The calculator will speak base 10, and you will get an error. Different calculators will give you different messages, but it's gonna tell you that there is no answer somehow. Think we covered enough. So -8 is an extraneous solution, and the only solution to this problem is 4, and that should do it. So I covered enough about logs, about the properties and the use of them with some examples. Thank you for watching. I hope that it was helpful. Hit the like button if you like it. Subscribe, comment below, as they always say. And if you like this video, hit the bell icon to be notified when I upload new ones. Until next time, peace. JaberTime.